Okay, so we are doing a literal ACT question, but two, we're going to use these to review old ideas, also to prepare you for the day. So today, one, have we done transformations in the past? Yes, helps us review. Two, today's all about quadratics, okay? So I'm about to introduce to you a new task. Kaden can, well first, go ahead and grab a seat for a second. Kaden, can you hand that to everybody?
Can I learn the old task, man?
I tried to get you to learn the old task. This new task will help you learn the old task if you trust me and do what I ask you to do. Well, it's always x minus h, so you need the opposite. But h is not always going to be negative. So, like if it had been...
Yes, I gotta show that.
I know they see me watching you, Bill.
Notice if it was already x minus 3, right here, in this case, h would equal 3. So h is not always negative, but it is always the opposite of what's right there. Does that answer your question? Okay. Carter?
I got that Carter from Brian.
One second, thank you. Thank you, Kia. There you go.
Don't think kids don't know about keys.
Dude, I didn't even do that.
There you go. Who? Okay, I will pass some out later. I'm assuming you're referring to yourself there. Okay.
Damn, we on 4?
Yep.
I ain't learned nothing. 1 through 3, I don't remember that.
We're not gonna have the class next semester.
Unit 1 was the stat stuff. Unit 2 was linear and exponential. Unit 3 was transformations and parent functions. Okay.
Now we're finna learn bias trend.
Now we're fixing to learn what?
Bias. Bias.
No, that's what we did Unit 1, dog.
Oh,
Literally, do you see anything on bias or unbiased on that sheet?
I wish I actually learned this one thing.
All right.
Not at football.
So, here's our agenda. We're going to do the gold rush task to help us learn about quadratic functions. Now, here's what I want you to understand. There's a whole lot that can be done and will be done in this class with quadratic functions. It's something you probably saw in Algebra 1 a good bit. I know for sure Miss Williams spends a ton of time on it. I don't know how, I haven't talked to Mr. Johnson about it, so I'm not sure how much he did with quadratics. I don't know how much Mr. Fulmer did last year with quadratics, I just don't know.
Oh my God.
But I know that Miss Williams did a ton with it, okay? Now, here's what we need to be doing today. We need to learn what a quadratic function is. There's multiple forms of a quadratic function. There's lots of pieces to a quadratic function. But if we don't know what a quadratic function is in and of itself, well, there can be a little bit of a creek. So today, we need to be able to identify a quadratic function in a table, quadratic function in a graph, a quadratic function in an equation. We're going to learn about some of those key things. We also need to identify all features of a quadratic function in a graph. And so when I say the features, I mean like domain and range. I mean x-intercepts and y-intercepts and the vertex and the line of symmetry. You'll notice all those key words are labeled right here. Okay, so those are the features that we're going to be looking for. Finally, the last feature, which isn't really new, so I shouldn't have it under target, but it's concavity. And so I'm going to introduce a lot of those words. Many of those things you don't need to know right away to be able to engage in this task. I just want to remind you, the way that I do classes, I present you a problem, and if you trust me and you work through the problem, you work on it together, I'm going to show you pieces of mathematics that you may not have seen before. So just tackle this problem. When you tackle this problem that I'm presenting to you, you will learn something new. And we'll be taking notes and adding some stuff to it. Now, here is the context, the gold rush, okay? So first things first, what is the gold rush? What was it? Okay, so people were finding gold inside of rocks.
Something in San Francisco.
It was really big in San Francisco in general. In what state?
I don't remember what state, but it got populated.
Yeah, we got San Francisco. It's in what state?
Miss Rich told me.
California. There we go. Yes. If you didn't know, let's learn that Gold Rush was all about California. Hey, that's why California, one, is actually such a rich state. Why it's such a huge population, has such big cities. is because of the gold rush. Anyone know when that gold rush was?
1949.
So close.
1849.
There you go. How'd you know 1849?
49ers.
Yeah, I was wondering if you knew that. So, the 49ers football team, that is based on the idea of the gold rush. Yep. So, a little bit of tie-in, okay? So, the gold rush is this idea that if you go, when you went out west, you search for gold and lots of people getting rich off the gold. But Dame Jackson's a shrewd man, okay? So, Dame Jackson has a little bit of land out west. And instead of panning and mining for the gold himself, he said, you know what? I'm going to rent some land out. First things first, real life context, I want you all to understand this. Renting will, from somebody, means that you will end up throwing some of your money away. Because if you rent land from Dan Jackson, are you guaranteed to find gold?
No.
No, but what is Dan Jackson guaranteed to do?
Get that money.
He's going to get some money, right? And so I understand sometimes we're not able to get out of renting, and so we have to rent. But in general, I want to encourage you and say, do your best to save up the money to be able to buy. There's lots of programs out there today that can help people buy houses when you can't fully afford it on your own, but make sure you're smart with your budget as well. Because if you are paying rent to somebody else, they're making money, but you're not building your own value, okay? So, but Dan Jackson, and again, if you can actually get to the point where you can buy an extra property and you can rent that out, then that means you will guaranteed be making money. So, Dan Jackson has a plot of land, and he's renting this land out to people. And how are you going to mark off your land according to this problem here? Look at the context. How are you going to, what's Dan Jackson going to give you to mark off your plot of land?
Rope and stakes.
He's going to give you rope, and he's going to give you stakes, okay? So what are you going to do with the rope and stakes?
Measure exactly. Measure 100 meters.
Oh, that's right. The rope has to be 100 meters, right?
Yeah.
Okay, so what are you going to do with your 100 meters of rope and your 4 stakes? You're going to create a...
Measure.
Yes, we're going to do some measuring, but what are we creating with it? Say it again. We were making a rectangle, right? So I do want to point this out. Is this a rectangle?
That's squash. It's a square.
Not a square, not a rectangle,
I like a trapezoid.
not a trapezoid.
It's like a rhombus. Rhombus.
It is close to a rhombus.
Good job, the one. White man.
Good job, Dan.
What is it?
Does anyone remember what these symbols mean? So this is not part of the lesson. I just want to recap this so that
It's not quick.
we don't remember seeing these triangles on side lengths like this.
Yes.
That means it goes that way.
Who does the young people do?
Parallel.
Just means that this side is parallel to this side, and this side is parallel to.
that side.
So what do we call it when the opposite sides are parallel like this?
Vertical. Quadruple. Horizontal. Quadruple.
Hey, listen. Parallelogram. Thank you.
I paid attention back in the day.
I see. So guys, this is a parallelogram. Now, that's not a rectangle though. A rectangle is a type of parallelogram, but what's going to be the key to creating a rectangle?
Side, up, down.
I ain't doing cheat codes, bro. Like, rectangle. What do I need to change about something like this to make it a rectangle?
Shift that one.
Like all sides of the
Length
same length.
times width.
Doesn't have to be all sides the same length.
No, so those are all.
Can someone come just draw a rectangle for us then? Just show me what a rectangle looks like.
I forgot, but we're gonna try.
We're gonna try.
What?
Do it for pear shape.
Wait.
How you doing?
Long rectangle.
Alright, so what makes this a rectangle?
Corners.
The corners, what about the corners?
Sure.
That's all.
They're right angles.
All the angles are...
Oh, well, mine ain't complete.
Not quite, but I'm gonna say that you attempted to make a right angle here. Is that fair to say?
Yes.
Okay, so notice are the opposite sides here parallel? Yeah, the opposite sides are parallel here. So this is a type of parallelogram, but for a rectangle, all of the corners have to create a 90-degree angle. Okay? So you're going to take your rope and you're going to put stakes in the ground, And then you're going to make sure that you set off a rectangle with your rope. Now you only have how much rope?
100 feet.
100 feet, okay? And so you need to figure out some dimensions that can work to give you the largest area. So, I'm just going to point, and so I'm going to give one more instruction, but what I want you to think about is this. When you set up your rope and you're trying to figure out the dimensions that give you the largest area, why would you want the largest area in the context of this problem?
So you can dig
So you
more
can cover
gold.
more land.
You can do.
So you have more land, so you have what?
Like more space, you can do for more.
So you have more space that you can dig for gold, which is going to give you a better chance of finding
Okay.
Go.
gold. There we go. Yeah, more profit, but better chance of finding gold. So you want to find the largest area, okay? What I want you to do is I'm just going to give you 2 or 3 minutes with your group at your vertical surface. I want you to draw out a few rectangles to figure out kind of what the dimensions might be. We're going to come back together, talk about what kind of dimensions do and don't work, and then I'll let you release you to work some more on this problem, okay? So just draw out a few rectangles and try to figure out some rectangles that can work that would have a perimeter of 100 feet of rope. Okay?
Tank.
So get up, go to your vertical surfaces.
Tank. I need my coffee. Dude. His ass Tank.
Hey, Tank.
Tank.
Hey, Tank.
Let's do this. Oh, there's no force, right? Okay, so yeah, Jack's on.
First line.
Yeah. So let's get up. Braden, up.
Up.
Carter,
On your
Layla.
feet.
Now we ain't cool.
Get on your feet.
Hey, I got you.
Dude.
All right. Okay. So let's talk about some of these because I want to make sure we learn from this. So if y'all can scoot to the side just a hair. All right. So right here, if I look at this rectangle, does this rectangle work for the context of this problem?
Maybe.
No.
No.
50-50.
Okay. So it has to add up to what? Okay. Why is that?
Because we only got 100 feet.
Remember, we only have 100 feet of rope. How many? Or not 100 feet. 100. Not inches. What? Meters. Okay.
Meters.
So, well, that's 100 meters right there, isn't it? Okay, so that doesn't work for us, unfortunately, okay? That's okay, we can learn from it. What about this one over here? Does this work?
Yes.
It adds up to what? 100 meters? Now, I do want to point out, this is actually very similar to what y'all did over there, except y'all did 40 along the base and 10 along the height. Is that okay?
Yes, it's the same
Yes.
thing.
It's the same thing, kind of.
One is going vertical, one's going horizontal.
Yeah, it's okay if some are vertical and some are more horizontal?
Me watching.
Yeah, right? You're right, but like we can rotate it, that's fine, okay? So, what about this 35 and 15? Because I want to pause, and I do want to point this out. A lot of times, I'm trying to speed this up for you in the long term. A lot of times students want to do the 10, the 40, the 40, and the 10, and like, oh, it adds up to 100. Beautiful. How do we know that 35 and 15 here works without even looking at the other two sides?
Plus 25, that 50 already. So,
So hold off on the 25, 25. I'm talking about this 35 and 15 here. How do we know that that's going to work out?
Is it because you add it together and you half?
Say that again, Brady.
35 and 50.
If that adds up to 50, what is this guaranteed to add up to, guys? 50, okay?
50 plus 50.
And 50 plus 50 is 100. So, hey, go on, chill. Okay, so Bev, what I was trying to get y'all to see over there, right? When you looked at that 40 and the 10, and remember see how I circled them over there? What's that 40 plus 10 under the 8s? That's 50, right? And we got 50 on the bottom two pieces, and then on the top two pieces, we got another 50 for a total of 100. So do you have to look at all four sides to figure out if it's going to add up to the 100 feet? No, okay? You just have to look at two of them. The base and the height. Do they add up to 50? If so, you're good to go. Now, we have a couple other examples over here on the 9s. I see a 25 by 25 by 25, or 25 by 25 is how I should say it. I see a 30 by 20. Now, there is always a debate. Is 25 by 25 okay?
Yeah.
Why not for a rectangle?
Because it's a side. That's just all square.
60.
So, please note, and hear me clearly on this. That is a square, right? But you remember how a rectangle, is a rectangle a type of parallelogram? Yes? A square is just a type of rectangle.
Cause it got 4 corners.
Well, it's not just that 4 corners. The 4 corners are all
Equal.
They are
right angles. There's a couple of other features there. So a square is okay. Okay, we need to recognize a square is okay. But my question or my challenge to you is what it says on here is to find the dimensions for your plot of land that gives you the largest area. But please notice on number 2 it says completely justify the dimensions for the largest plot of land. You need to develop thorough and clear evidence that supports your answer. Oh, it doesn't say it on there. Maybe it's on the back. Oh, it is on the back. You need to create at least 2 mathematical representations to justify your answer. So please hear me very clearly. Yes, I know this is about the gold rush, but I've also already told you we're trying to discover something mathematical. What thing mathematical are you trying to discover? We're trying to discover quadratics. We're trying to get the largest plot of land, right? But through this task, I'm trying to get you to understand quadratic functions. Don't lose sight of that. And so we need to create multiple mathematical representations to justify our answers. So what are the mathematical representations we can construct? Tables, graphs, equations, our algebra. What else? Verbal and pictorial, right? Now I will say, please don't let pictorial or verbal count in this case. I want you to look at the other 3. I'll explain why later. Yes, Bev?
How would you graph this?
It's a fantastic question. If you're not sure how to graph it, what could you create first maybe to help you get to the graph? Maybe a table, maybe an equation with a parent function or something. If you're not sure, right, create something you do know how to do. Okay? So if you're not sure, create something you do know how to do. That's why the suggestion I'll give here. So you have some rectangles there. We now need to find the largest area possible. By the way, I should have mentioned this earlier. How are we going to find our area?
Length times width times.
So be careful. Length times width times height gives us our volume. We're not talking about volume, we're talking about area. So what I would do, base times height. Okay? There's many of us have probably done length times width, right? That's how we usually do area. But if I do area, I always do base times height. And here's why. And this is not part of this lesson, but it will help you long term with some of the ACT stuff, other things like that. Does anyone know what the area of a triangle is? Do we remember that formula?
Yes, I don't. I do, I don't.
Anybody remember that formula? That's Pythagorean theorem. So, no, that's not close enough.
Is it just
I mean, it
saying-
is a triangle.
It does relate to a triangle.
Something like
It's 1/2 times
B.
base
Base
times
width.
times height. Okay?
Oh, this is gonna figure
Okay.
out from middle school.
So area of a trapezoid. This is much less remembered, but I want y'all to pay attention to this. 1/2 times base 1 plus base 2 times height. Okay? Hopefully. And the area of a parallelogram is equal to base times height. What do all of these formulas have in common?
They all have base times.
They all have a base times height. Remember earlier, even when you were talking about length times width times height? For that volume idea? Okay? So that's how we calculate volume. This length times the width, what that actually is the area of the base times the height. Volume, area, all of it can be broken back down into base times height. And specifically, like with a triangle, what do I get when I cut a rectangle in half?
2 triangles.
Get 2 triangles. So what's the area of this one triangle? Same as the other one, but it's what? It's half of the base times the height. That's where that formula is coming from. Because if you take a rectangle and cut it in half, you get a triangle. Same thing with parallelogram. So base times height is how you're always going to see me write it. So all that to say, you don't have to remember all that. It's just why I use base and height. Base of 10 times height of 40. What's the area of this plot of land? 10 times 40.
400.
400.
Come on,
Okay.
Ken.
So, now I want you to go back to your plots of land. I want you to use mathematical representations to justify what are the best dimensions to get the largest plot of land. Let's get after it.
Oh, we already did.
Can I get a
We'll put it up.
That's not the largest. And even if it was, I would tell you it's not, so that you have to do more work to justify yourself. You need to discover what a quadratic is.
Come on.
I know.
Let's get to work.
Stay back, let's get to work.
Oh my gosh.
You're capable
Hey.
of doing the work today.
Yo.
Hey, Tank. The area.
I specifically told you, don't forget, we're not just trying to find the area, we're trying to discover a what?
Larger, bigger.
No, there's something else. What are we trying?
Quadratic.
The quadratic function. Hey guys, the whole point of this, I told you from the beginning, I wasn't trying to hide this. The whole point of this was to discover the quadratic function. Yes, we want to find the largest area. Alright? But we want to discover the quadratic function. Now, I want y'all to look over this, because this is actually the first time that this has ever happened, where so few people have, or few groups have done this. But this group made a graph. By the way, Dwan, Kyle, come on over this way. Carter, come over this way. Stop going near my stuff. I hate to say this, but I don't trust you near my stuff. Where is my remote? My presenter remote. Carter, where's my presenter remote?
Got friends. That's why you don't trust him.
Why don't I trust them?
Got no friends. Look away. I don't know where it's at.
Anyways, right here, okay? So when I look at this graph, what tells me that this relationship, looking at the area, was quadratic?
This is going up. The parabola.
Oh, say that one more time.
The parabola.
The parabola. Now I'm going to modify this just a hair to make sure it's a little bit more accurate. Should have been 25 by 25 is 625, so a little bit further over this way. Notice y'all did skip this point over here. We want that one. Do notice, so first off, what shape do we have?
A U.
No.
One parabola.
It may look you like, but that is a what?
Parabola.
That is a parabola too. So this is a parabola.
All that.
We got a parabola here. That's a quick way to know it's quadratic. We've already dealt a little bit with parabolas, haven't we? Yeah, right? We dealt with quadratics in the parent function and the transformations. So we've got a parabola here. Now, I started pointing this out to a lot of groups, and I want us to focus on this first. How did we know, specifically this group, I talked about this with y'all, how did we get these points so quickly? What was happening here? You flipped them, right? And when we flipped them, we got the same thing. Hey guys, what's another way to say that we flipped something and we get the same thing?
You have to inverse.
Opposite.
I'm looking for that one. I'm looking at a reflection here, right? But what do you have to have in order to have a reflection? There has to be some kind of line there.
Vertical. I mean,
Horizontal
this
axis.
is the. Dude.
That is a line, but not this type of line. Okay, let me ask a different way. One of the ways that we typically talk about beauty, or the measure of beauty, is we talk about someone's features are very what?
Beautiful. Wow.
The same on one side as the other.
Symmetrical?
Very symmetrical. Like, the idea of symmetry is important for that, right?
Yeah.
Okay, the same on one side as on the other. When I look up here, we said there was a reflection, right? It was the same on one side as on the other. So what does that mean? There's a line of symmetry somewhere,
In the middle.
right in the middle. You want to come draw that line of symmetry real quick?
Straight
Draw it
down.
with a dash line for me.
To number 30.
Okay,
That's a little.
that's pretty good.
Yeah, I get it.
Yeah, I like that. All right, so hey, what happened to that red marker that's over here?
Got white and dreadheads.
Hey, chill out.
Oh, that's okay.
There was one just sitting over here. I was
Yeah,
going
why
to try to
can't
do something in a different color. All right, look, this right here. This is known as a line of symmetry. Notice the stuff on either side of that line of symmetry have the same y values, right? Every point on either side has the same exact y value. So when we are talking about a parabola, an important concept, an important term is the line of symmetry. You may have also heard it called an axis of symmetry. Okay. Ms. Williams called it an axis of symmetry. Either one is perfectly fine. Axis is what is very traditional. It's what I grew up using. I've just seen more and more resources recently calling it a line of symmetry. Because it is a line, right? Okay, so an axis or a line of symmetry. Now I want y'all to look at your proficiency scales. Does anyone see any terms in that foundation piece that we might be able to see in this graph up here?
Wait, what were we looking for?
Any terms, any features of this function?
Vertex form at.
Well, so that's a form. I'm talking about a feature. Like, and I heard. Okay, we talked about a line of symmetry. That's important. What else? Vertex. Okay, where's the vertex on this graph?
The middle, the
25.
Where the line of symmetry starts.
So where that line of symmetry intersects the graph, this right here is called a
Vertex.
vertex. Okay? What's a way that you might describe that vertex? Like if someone asked you to define and say, hey, this is what a vertex is, how would you describe what a vertex
first
is?
of all,
Is it
I explain it to them.
The middle.
How are you gonna explain them?
I explain to them.
The, what part of the
Good.
middle?
So I heard someone, so hold on to that. I heard someone say it's the top, right? Or it's the, but notice, if it looks like this, where's my vertex this time? It's at the bottom, right? So that's going to be the difference between a maximum and a minimum. But what were you saying?
Turning point.
That's a turning point, right? The vertex is the turning point. There's a lot more that we can say and define it as, but in an Algebra 2 class like this, that's perfectly fine, okay? So the vertex for a parabola is the turning point. It can either be, if it's at the top, does anyone know the term we use for that typically? Someone said it. That's the maximum, right? If it's at the top up there, it's the maximum. And if it's at the bottom, it's a minimum, okay? But it is a vertex, okay? All right, so we got a vertex, we got a line of symmetry. What else do we have?
Wait, say that again.
What else? What other features does this parabola have? Ah, some x-intercepts and y-intercepts. Where do we see x-intercepts?
Down there.
To the left.
So this 50 right here, that's an x-intercept. How do we know, so hold on to that. How do we know that this is an x-intercept? This is where,
Things get tricky.
it's not where it starts.
Hits the line.
So it intersects the what?
X-axis.
The x-axis. Notice, literally, the parabola, the function, is intersecting the x-axis there. Does anyone see any other x-intercepts? Bev, you mentioned the what?
Origin.
The origin right here. What would I call this point at the origin?
The y-intercept started. No, it started.
It is a starting point, but does that mean it's not a y-intercept?
Nah, you can finish where you started from.
Why would it be y-intercept if it's on the x-intercept?
Ah, so, hey, I need y'all to pay attention to this, because what's nice pointing out is it's actually intersecting the x-axis, isn't it? But is it also intersecting the y-axis?
Yes.
Wait, so if it hits the x-axis and the y-axis, we would call it an x-intercept and a y-intercept. Notice that point, at that point, the parabola intersects the x-axis and the y-axis. Okay, so here's what I need y'all to do at this point. There is space on the back, but you can put it also on the front. We're going to talk about the other representations, but I need you to get this graph down of this function. I need you to label these different features, right? I need you to make sure that you have a graph and that you understand why do we know this is a quadratic function off this graph? Because we have a,
Parabola.
You got a base?
or more properly called a parabola.
Yeah, I can't
Yeah.
believe I can't
Okay.
believe it. Miss
So-
Williams got it stuck in my head.
So, guys, we got a parabola, we got a quadratic. Make sure you get down these features. Bev, do you need a pencil, bro?
I do.
Well,
Bev, do you need a pencil?
mechanical pencil.
You got one? Okay.
Can I?
Alright, hey guys, make sure you copy down the sketch of that graph.
Are you want to-
Precisely graph those points. Yeah, dude, you're shorter than me. Congratulations.
Sure.
Okay? Who needed a pencil still? Sanaya?
Me, I'm trying to grab these.
Also, really quickly, I do want to point this out. Hey, over here, there are plenty of tables. Hey guys, pause for a second, listen here. There are plenty of tables around here. You didn't have to do this. Y'all can do what y'all do with just kind of create a table, use it to help you graph. But you will want this table soon, and I would put this next to my graph. So please do notice this has a base of 0, a height of 50, an area of 0. Then 5, 45, 225. So notice they got their base in one column, their height in a column, and their area in a column. Please copy down that table or up at the front, but this one is complete. So I would do this one over here. So go ahead and put that table. put that graph, I'm going to talk through that table later, okay? So I'm going to talk through that table later, but make sure you have this graph and all of its features there. Trent, you can't learn a single thing if you got your head down. It's the easiest thing to pick up a pencil and write.
Pick up a pencil, pick up the
Okay. Now, so again, we already had it. Remember, you got it to be able to recognize when you have a parabola, it's what type of function? Quadratic, right? And we got to be able to look for the features of that quadratic. When I say the features of the quadratic, what am I talking about? The line of symmetry. The what? The vertex. The x-intercepts and the... Oh, sorry. There's actually one more thing I just remembered I forgot to talk about. So we've talked about the idea of reflections before, right?
Yes, sir.
Okay, so please notice when we talk about this later, there has to have been what to get this function here? There had to have been a reflection, right? There had to have been a reflection. And this is a term we have not used yet, but what we're going to call this direction, so like, would we say that this parabola is going down or that the parabola is going up?
Upward.
Down.
What?
Why do you think it's upward?
Because it looks like it's taking up.
I got you. So let me say this a different way. We have two options. We have concave
Concave up. And
down
concave down. Yes.
like
Concave up.
a frown.
And concave up like a cup.
Yeah.
Yes.
Okay, so did Mrs. Williams use that as well?
Yes.
Okay, so concave up
Like a cup.
like a cup. Okay?
Like
I made a balloon.
So concave down like a frown, does that look like a frown or does that look like a cup?
okay, it looks like a frown.
It looks like a frown.
Okay.
Concave down like a frown, so we need to know about concavity.
She got a picture.
And then concave up like a cup. Which it doesn't look a ton like a cup, but if I pour water into here, will it hold the water?
He gonna do so.
He said up like his butt. I don't know what that means.
So guys, concave up like a cup, concave down like a frown. You gotta know the idea of concave up and concave down. We're gonna use that
So you
soon.
look like a clown. Yes, sir.
Okay? Do notice it's gonna be concave down when you have a what in there?
That's
A frown.
Think about the transformations we've already discussed. A negative, but what kind of negative? Creating a reflection, right? Because if you're subtracting, we mean is multiplying by a negative. Okay, so now we need to come and look at this table. I need y'all to remind me of something. So this is actually really important. We studied linear functions before. What kind of rate of change did a linear have?
Look, I don't know.
Constant additive rate of change.
Hopefully this sounds familiar, that a linear has a constant
Additive.
additive rate of change.
Or a constant difference.
An exponential function has a what?
Constant multiplicative rate of change.
Constant multiplicative rate of change. So guess what? All functions have some type of rate of change. Hey, Dewan, can you close your iPad?
Yes, we can. I will.
Thank you. So when I look over here, I need to be looking for a rate of change, okay? What's happening to go from 0 to 225?
It's changing.
Thank you. By how much?
About
By how much, Carter? It's adding by 225.
You said 0 to 25.
0 to 225 is plus 225. What about to go from 225 to 400?
Plus 220. Plus 400.
425.
Hey guys, y'all got calculators around the room.
Calculus.
What you could do is you could do 400 minus 225, and that might tell you the answer.
Should I erase what I wrote right there? Right that graph.
Multiplication.
Is how much? So we're adding 175 here. How about to go from 400 to 525?
Add 125.
Adding 125. How about to go from 525 to 600? Say again.
65.
It wouldn't be 175. It's how much?
75. 65.
Capable.
You said it a second ago.
75.
It'd only be 75.
Girl, where you going?
So I want to point this out. At least so far. We're going to talk about this more in a second. Is this constant additive?
Yes, it's all got 5, it's a pattern.
But is this constantly adding by the same amount every time?
No.
Yeah, it's definitely
No.
not the same.
It's
Is it
not-
adding?
5,
Yeah. But is it
It's not.
constant additive? Huh?
No.
It's neither so far, but hold on, we already know what type of function it is. It's what? Quadratic, right? Okay, how about you go from 600 to 625? Plus 25. What about 625 to 600? Maybe minus 25. Because remember, we said this vertex was the, what did Brady call it? He called the vertex the turning point, right?
Turning point.
I'm sorry. My mom told me about
You good,
what's it
bro?
called? Tire. And it can explode. And I don't want to pick me up. It's just gonna explode.
It's gonna die.
Please get brother tomorrow. Change that, Mr. King.
Look at my baby.
Look at that look.
We've had too many chances.
I'm sorry.
The crusty
I
crab.
don't want to die on the way home. I can show
He's in
you.
the Krusty Krab.
You ain't gonna die on the way home. It's something you could have checked after the bell rang, right?
I'm sorry. I'm just trying to make sure before 315 hit.
A tire not gonna wait for 3:15.
600 to 525, it's not gonna change anything in the next 10 minutes. Alright, so here's the thing. Can we all agree it's not constant additive?
Anyhow, right there.
In the kindest ways. You trying to come up with excuses.
What?
Not really. But that's an excuse, not why you're doing it.
He knows you will.
Alright guys, hey, real talk, we gotta pay attention to this. Is this constant additive?
No.
No, okay? Does anybody see a pattern though to what's happening here?
It's flipping from positive to the negative.
Eventually, at that turning point, but there's something else that we're missing.
2 to 7.
2, 1, 1, 7, 7.
It's opposite.
Hey, can someone tell me what 225 minus 50 is?
21.
You said what?
What's 225 minus
150.
50? You've got calculators.
175.
Wait, this 175?
Yes, Mr. King.
Hey, what's 175 minus 50? You mean this 125?
So,
What's 125 minus 50?
75.
You mean
that 75 right there?
25.
You mean that 25 right there?
Light bulb.
25.
So,
I money would've
here's what I legitimately need y'all to see, and I need y'all to write this down in a second.
Our money would've been-
Hey,
I had to take a picture, man.
hold on. This orange, right? I need y'all to hear me get on this. This orange, this rate of change, was it constant additive?
Yes. No, because all of it negative.
Well, they're changing. They're not constant, they're changing. But what about this purple?
Constant.
That is constant.
Subtraction.
Subtraction, but remember,
Division.
subtraction is a type of
Addition.
addition,
So it's a constant additive rate of change.
not a rate of
Come
change.
on, what is
So hold on to
that?
that. Pause. This purple is constant additive.
Hey,
What type of function have we studied in the past that was constant additive? It was linear, right?
Linear, yeah.
Because here's the thing.
Often said
Only this orange is my rate of change. Let me say that again. Only the orange is my rate of change. If this is constant additive, how could I describe this orange? What was constant additive earlier?
I did.
The linear.
Linear. So if this is constant additive, how can I describe this?
That's half.
That's,
Is it more? Wait.
that is linear,
They in pairs.
okay? But that's not a function, is it?
No.
Linear what? What are we doing with these numbers? We
Pairs.
are adding, so it's a linear additive rate of change.
I did say rate of change now.
Hey, after the bell, can I take pictures of my phone? My bad.
You could also just write it down. You got 8 more minutes. So linear additive rate of change. Guys, here's what I need y'all to hear me clearly on. If you want to know if you have a quadratic function, one of the telltale signs, right here, what do we have around the vertex? Hey guys, right here. In a quadratic, in the table, what do we have?
And the table, we got 25.
Speak with your check.
Like a symmetry.
Speak with your check.
Hey guys,
Symmetry.
I need us to focus. I need us to learn this.
symmetry?
Guys, symmetry in the table, listen, symmetry in the, holy crap, can I talk? Trent, in the graph we had symmetry, right?
Yes, sir.
In the table, do we have symmetry?
Yeah.
Yes. On top of that, and I want to point this out, how many x-intercepts do we have?
Zero.
No.
One.
1, 2. But here's the thing. This idea of the symmetry in the table, this idea of the x-intercepts and the two x-intercepts doesn't always work. What does always work is all quadratics have a linear additive rate of change. You've got to recognize that all quadratics have a linear additive rate of change. So how do I know when I have a quadratic as a graph? I've got a parabola with all those features.
You got a parabola.
How do I know when I have a quadratic as a table? It has a
Linear.
additive rate of change. And remember, the way I found that was I looked at my differences. Hey, right here. This is constant additive. And what type of function had constant addition?
Linear.
Linear. So this, orange, not a function, it is a rate of change. So it's a linear additive rate of change. Final thing, because I got 5 minutes left.
Well, you're-
Okay?
It's already said that.
Not, but I'll leave that there in a second. I need your attention on this. Look, when we look at this area formula, several groups worked on this. So if you didn't fully work on it yet, I apologize, you're going to be a little bit behind. But one of the things I talked about with multiple groups is if I take away the base from 50, that gives me the height. Notice, what's 50 minus 10? 40. What's 50 minus 15? 50 minus 20.
30.
So if I take away the length of the base from 50, I always get the
H.
which is the height. A property that you've learned in Algebra 1 and you even learned in middle school some was substitution. If h is equal to 50 minus b, what can I substitute this in for? No, what can I substitute this in for?
H.
H.
To the H, to the B, to the H.
That creates this equation.
Dude.
Okay. Alright. I need you to pay attention to two things, guys. We've still got 4 minutes. Chill. First, I want to point this out. This b is linear. That's just b raised to the first. That's the idea of a linear. 50 minus b to the first, that is also what? A linear. One way to see a quadratic that we're going to talk more about is a linear multiplied by a linear. That is a way to talk about a quadratic. It's a linear function times a linear function. Second, if I distribute this, I am left with 50b minus b squared. In this equation right here, what tells me that I have a quadratic? The square tells me I have a quadratic. Okay? So remember, the whole point of today was to learn about quadratics. And so what we need to learn is we need to figure out how to recognize a quadratic from a graph. That's usually the easiest. That's where most people are most comfortable. But we also have to look at the rate of change in the table. And finally, we got to look at the equation. If you have a linear being multiplied by a linear, what do you have? Quadratic. If you have a squared as your highest power, what do you have? Quadratic. These are the telltale marks of what a quadratic is. Hey, pause for a second. Y'all still not done. Hey, Carter, keep your stuff out. For real? You just gonna ignore me like that?
What?
I said keep your stuff out.
What?
Because I'm still teaching. Look, here is why you would want to be able to write an equation. Because here's the thing, was that equation the easiest?
No, it wasn't.
No, it's not. But let's say I have a graphing calculator. On the graphing calculator, I'm going to put 50x minus x squared. Now, I can't see that very well, but I'm going to change my window. And we'll practice with this some. Notice I went from a base of -5 to 55. What was the maximum area that we had? Was it 625?
625.
I'm looking for.
And how does that graph compare to what we graphed by hand? No, it's exactly the same, doesn't it?
That's a pop out.
So guys, if you had been able to write the equation from the beginning, would that have made things easier?
Maybe.
Remember, most teachers try to teach directly the equations, but because the equations do make things easier, but they're not the only way. Notice, you can actually take this graph and find the maximum, that vertex. Do those numbers look familiar?
They do look familiar.
Yeah, they do.
They do, don't they? It's 25 by 25 gave us an area of 625, right? So guys, when you understand quadratics better, you can write these equations quickly and efficiently by hand. And so that's what we're going to try to work towards. All right,
And
that's all I got for today. Make sure you go ahead and start looking over your notes. You need to know what a quadratic looks like. Keep it up. I'm about to. Okay, you need to be able to identify what a quadratic looks like in tables, graphs, and equations.
I was not here.
On that C, that sign, on that C, that dollar sign. Throw it up, throw it, I'm on fire.
Thank you.
Thank you, Mr. Kennedy.
Yes, sir. Hey, babe, you feeling better?
Yes, sir.
Okay.
Thank you.
Yes, sir.
There's a lot of dudes skipping.
You say there's a lot of dudes skipping?
Yeah, there's a lot of people